So welcome to this lesson where we're going to talk about convective clearance. In the last lesson we talked about diffusion, and that's one way of eliminating a solute from the bloodstream when you're doing dialysis. We're going to talk about another way, and this is called convection. Now we're going to make a comparison between one of the best convective machines we have, and this might be familiar to you if you've seen some of the other tutorials on this website, and this is our Glomerulus. We're going to compare that to a dialysis filter. Alright, here's our traditional compartment 1 and compartment 2, and let's annotate our filter. We've got blood flow coming into compartment 1 and then leaving compartment 2. And let's see what's happening over here. We've got blood flow coming in this way, a lot of it, and only some of it coming out. Here's your glomerulus, and there's a pressure that's applied to the glomerulus. That pressure is the difference in pressure between your afferent arteriole and your efferent arteriole. Whatever that pressure difference happens to be is called the intraglomerular pressure, and the intraglomerular pressure is what forces fluid into the tubular space. So what we have here is one of the most basic convective models. It's actually what is occurring in your kidney. A pressure is applied at the afferent arteriole that's greater than what's at the efferent arteriole. The difference in that pressure forces fluid through this membrane into the tubular space. That's convection, and now we're going to see how that works here in the filter. You notice that in this filter I have not done anything to compartment number 2, because what's happening is you're not having diffusion in compartment 2. There is no dialysate fluid going in the opposite direction. You're applying a pressure. Your machine is applying a pressure at this point right here that's greater than the pressure it's applying at this point right here. The difference in that pressure is going to force the fluid that's in the blood into compartment number 2 and then out as waste. That's how convection works. It takes advantage of a pressure gradient to force fluid through a membrane into the next compartment. In the case of the filter, it's compartment 2 and then out as a waste product. In the case of the glomerulus, it's into the tubular lumen and then out as a waste product. So how do solutes come across when you're exerting a pressure difference? Convection causes solutes to travel with the fluid that's being moved. And actually that's what the definition of convection is, at least one simple definition. The movement of solutes through a solution or a fluid. And in this case the fluid is the water that you take from the blood. So solutes move along with the water. They're being carried with that ultrafiltrate or water through from compartment 1 through the membrane to compartment 2 and then out. So how do solutes move? Now let's look at this a little more closely. Let's look at our filter and then we'll get back to the glomerulus. And here's our membrane. And we said here's compartment 1 and here's compartment 2. Blood flow is through compartment 1 because there's a pressure being applied at this point which is greater than what's at this point. You're going to get fluid to move across. Now that fluid is going to carry with it solutes, and it's going to carry solutes of all different sizes. Small sizes, some solutes that are a little bit larger in size, and then of course the largest solutes of them all. Now, unlike diffusion, you don't have to depend on the intrinsic activity of these solutes, because these solutes are not moving based on their likelihood of contacting the membrane and crossing the membrane. These solutes are moving based on how much ultrafiltrate or water, the green arrow, is being shifted from one compartment to another. So for convection, you notice two things. Intrinsic activity does not matter. In other words, the size of the solute does not matter. As long as the solute fits through the pores of the membrane, these are the pores right here, they will all travel at the same rate. And that's the key point of convection. Solutes travel at the same rate. Now, that doesn't mean to say that you're going to have the same concentration of large solutes in your blood as you do small solutes in your blood, because you're not starting out with the same amount of small solutes and large solutes, but your clearance, which is the rate at which you eliminate these solutes, will be the same when you use convection. So when is convection useful? It's useful when you have larger solutes, solutes that would not diffuse easily because their intrinsic activity is too large. Certain cytokines, in cases when you have sepsis, those cytokines may be removed a lot better with convection. Lactate, it's a larger molecule and therefore easier to remove with convection. If necessary, you could do immunoglobulins. Now remember, immunoglobulins are very, very large molecules, so they generally won't fit through these pores. But if you had a dialysis filter that had humongous pores, immunoglobulins would move at the same rate through convection. And the same is true for cytokines. Not all cytokines are small enough to fit through the pores, but if they are, they will move at the same rate as the smaller solutes. So in general, you can try to eliminate larger molecules. Sometimes you have middle molecular weight uremic toxins. Of course, those are not yet identified, but you cannot assume that all uremic toxins are small. Some of them are middle molecular weight, and they can be removed at the same rate as those small ones if you do convection. So that's convection. This is very similar to what's happening in the native kidney and the transplant kidney. Unfortunately, if you replicate this in a dialysis machine, despite it being very similar to what's happening in the glomerulus, you don't get any extra mortality benefit. But it's a very easy process to undertake, and it's very physiologic in the sense that a lot of what's happening in pushing fluid and solutes across one compartment to another is exactly what's happening in the native kidney. And that's today's lesson. Thank you very much.